The equations behind me are called sum and difference formulas or sum and difference identities. And let's just kind of get the lay of the land here. They look a little complicated at first, but they're really not any big deal. Notice this is the sign of the sum of angles, and this is the sign of the difference of angles. And they're associated with a certain expression involving sine and cosine over here. And here we have the cosine of a sum, cosine of a difference of angles, and then an expression. Tangent of the sum, tangent of a difference, expression. Okay, so that's the idea. Now, these formulas or identities, we can think of them either way, are useful in both directions. That is, sometimes we'll use them in this direction and sometimes in this direction. Sometimes we'll have an expression like this and we'll rewrite like that. You see, and sometimes we'll have this and we'll rewrite like that. Now, in using these, you'll begin to notice a pattern, and the pattern will allow you to remember these rather easily. And I'm not suggesting that you go through and memorize these. I am suggesting that you write these down or refer to them in your textbook when you first have to use them. But be aware, be conscious of the pattern situation involved in these. And with that consciousness, the memory of them will come back rather easily. For example, in the sign of a sum and difference, we have sine, cosine, cosine, sine in both of them. And we have one is plus, one is minus. That's the only difference between these two expressions. And this is the expression for the sign of the sum of angles, and this is the expression for the sign of difference of angles. And in this pair, there is a nice little pattern. Now, this is the cosine of a sum, cosine of a difference, but cosine, cosine, sine, sine. Cosine, cosine, sine, sine. So that part of the idea is the same in both of them. And when we're talking about the cosine of the sum of angles, we have a minus sign here, oddly. And when we have the cosine of the difference of angles, we have a plus sign here, oddly. All right, and then with the tangent, the sum and difference of tangent of the sum and difference of angles, similar kinds of patterns emerge. We have fractions in both cases, for example. And when we have the tangent of the sum of angles, it's the tangent of one angle plus the tangent of the other angle in the numerator. And then it's 1 minus the product in the denominator. And when we're talking about the tangent of a difference, it's the difference in tangents of the two angles, and in the denominator 1 plus the product. Okay, so anyway, a lot of patterns emerge in this situation. Here's one way that these formulas or identities can be used. We can evaluate exactly the sign of, for example, 105 degrees if we rewrite 105 degrees as the sum or difference of some familiar angles. So we can rewrite this as the sine of 60 degrees plus 45 degrees. You see, and then implement one of our formulas over here. Well, it would be the formula associated with the sine of the sum of angles. Now, so we refer back to that formula, and it's the sine of the first angle times the cosine of the second angle, plus the cosine of the first angle times the sine of the second angle. And then we go through the process of evaluation by just kind of using our little triangles and so forth, and we would write those triangles down maybe on the side or something like that and find the sine of 60 degrees to be the square root of 3 over 2. And the cosine of 45 degrees is 1 over the square root of 2. And the cosine of 60 degrees is 1/2. And the sine of 45 degrees is 1 over the square root of 2. And now it's a matter of cleaning up algebraically. This becomes, now just multiplying the two fractions, this is the square root of 3 over 2 root 2. And here this is 1 over 2 root 2. Now from here there are really two ways to rewrite this expression. And I think it's important that we recognize those two ways. Actually, there's more than two ways. There are a number of ways of rewriting this. And it's important to know the difference between them because the answers in your textbook take a particular form, you see. And a lot of times you'll get the same answer on your paper, but it'll just be in another algebraic form. And you're going to think that you've made a mistake up in this part of the problem when in fact you've just made a slight mistake maybe or not a mistake at all in the expression of your answer. So it's really important to be able to recognize that things that may look quite a bit different are precisely the same. As an example, in these two you recognize that we have common denominators of 2 root 2. So I could take out 1 over 2 root 2 from both of these fractions. I could factor them out, you see. And then what would be left would be these numerators, the square root of 3 plus 1. You see, now another way is to say, well, we have common denominators, so let's bring the fractions together, and we have the square root of 3 plus 1 in the numerator, and the denominator is 2 root 2. And then another way to deal with both of these is to rationalize these denominators. So a lot of different looks, but all equivalent forms to one another. It's going to depend a lot on the preference of your teacher as to how you want to leave your answer. Here's another situation. Now, notice this one involves a pretty big angle, and we want an exact value for the tangent of 195 degrees. And we can use a sum or a difference formula. Now, it's important when the angles start to get big like this that we have some grip on all of the reference angles that are the same as or are related to our familiar angles of 60, 30, and 45 degrees. Now with 60 degrees, it's 60 degrees in the first quadrant, but 120 degrees in the second quadrant. This 120 degree angle has a reference angle associated with it of 60 degrees. And when we go to the third quadrant for a 240 degree angle, we're talking about also a reference angle of 60 degrees. And 300 degrees is associated with a reference angle of 60 degrees. See, that's what I mean. And for all of these, it's a similar kind of thing. Now, if we have a grip on this, or we are able to refer back to a chart that might look like this, then we can rewrite 195 degrees fairly easily. Just kind of find the sum of any two of these, it gives 195, or the difference of two of these, it gives 195. Now, one such relationship would be, 225 degrees minus 30 degrees for 195, you see. So it's this with that. Okay, now I know I can use these because they are related to familiar angles. All right, now with that in mind, here we go. So I'm thinking of rewriting 195 as 225 minus 30 degrees. And now I'm going to implement the formula for the tangent of the difference of angles. And I don't recall it, so let me just look back over. I'm just going to refer back over there and write down the fraction. Now, I seem to remember that it was the tangent of one angle minus the tangent of the other angle over 1 plus the product of those two. See, and just go very carefully through the problem just like this. Now we understand that this was related to the 45 degree angle. Now it's well, let's see, where is it in our coordinate plane? Now we might have to make some sketches here or something like that. But 225 degrees turns out to be in the third quadrant. All right, and as a third quadrant reference angle of 45 degrees, we know it's the 1 square root of 2, but in the third quadrant, remember, it's -1 square root of 2 for that right triangle. All right, and tangent is -1 over -1. Okay, it's a third quadrant angle, and the tangent is positive in the third quadrant, so it's +1. You see, that's how we kind of work our way through or think our way through this situation. So that's 1, and then minus, now tangent 30 degrees. Well, we could make a little reference triangle here if we want to. Make this the 30 degree angle, you see. And now we have, that's 60, and we have the 1, 2 square root of 3 idea in this context. Or we could separate it out if we want to do that. That's fine. But the tangent then of 30 degrees is 1 over the square root of 3. Of course, it's positive because we're in the first quadrant. And this minus sign is that minus sign, and that's just positive. Okay, then we have 1 plus. Now, tangent 225, we've already figured that out. That's 1. And then the tangent of 30 degrees, and that's 1 over the square root of 3. And now it's all a matter of cleaning this up. You see, and let's see, cleaning that up, well, this is 1 minus 1 over the square root of 3. This is 1 plus 1 over the square root of 3, a complex fraction. There are several ways to deal with it. I think the easiest way, though, is like this. Just take this big old fraction and multiply it by the square root of 3 over the square root of 3. And I'm choosing this because the square root of 3 is the common denominator for all of the little fractions within my complex fraction. So as I multiply through, I get the square root of 3 times 1 and then the square root of 3 times this. I'm just going to work out to the left side here because I have a little room. But it's the square root of 3 times 1 is the square root of 3. And then the square root of 3 times this fraction, the square roots of 3 will cancel and I'll be left with minus 1. And then in the denominator, root 3 times 1 is root 3. And then a cancellation occurs here and we have plus 1. Well, we're still not finished. We still have more to do here. Well, I should say, we may have more to do here if it is the preference of your teacher. You see, we have a radical in a denominator, and in our past experience, we have had to rationalize here. Now, if we need to rationalize, let's recall that process. We have to multiply, since we have a binomial involving a radical, we have to multiply by the conjugate of that denominator. So we're taking, and I'll just start with that fraction, square root of 3 minus 1 over the square root of 3 plus 1, and I'm multiplying both numerator and denominator by the conjugate of this, which is the square root of 3 minus 1. So in both numerator and denominator, I'm doing that. Okay, now, in doing that, we're multiplying binomials, so the safest thing to do is to introduce some parentheses to enclose all of them. In the numerator, we have root 3 times root 3, that's the square root of 3 squared, or root 9 if you'd like to write that down, but I'm just going to express it this way. For the middle term in this product, we have minus 1 root 3, another minus 1 root 3, that's minus 2 root 3. And then for the last term, plus 1. In the denominator, it's even easier. Square root of 3 times the square root of 3 is the square root of 3 squared, and then minus 1 squared. All right, back into the numerator, this becomes 3. Squaring the square root, you see, gives us the radicand. So we have 3, then minus 2 root 3 plus 1. And in the denominator, we have, this becomes 3 minus 1. So we have 3 plus 1, 4, minus 2 root 3 in the numerator. And then 2 in the denominator. This 2 divides both parts of the numerator. So let's see, when we divide into 4, we get 2. When we divide here, the 2's go out and we have minus the square root of 3. Well, most of the manipulation in the problem had to do with resolving this radical situation and not so much using the sum and difference formulas, it turns out. But at any rate, what we've accomplished here is an exact value for the tangent of 195 degrees, the exact value of tangent 195. Okay. Here's another use for the various formulas. We can use the formulas to verify either an identity or some kind of conjecture that we have made in the past. And one of the things that we've said in the past is that cofunctions of complements are equal to one another. Let's prove that. You see, we'll say that the sine of, now this 90 minus theta is the complement of theta. So theta and 90 minus theta are complements. So here is theta, here's the complement of theta, and we have cofunctions involved here. You see, and we want to prove that they're equal. Well, to do that, we'll go through the proof of identity process. We'll work with one side of this. Here we have the sine of the difference of angles. So I'm going to use the formula for the sine of the difference of angles. And you may recall by now that it's the sine of the first angle times the cosine of the second one, minus the cosine of the first times the sine of the second. And now let's evaluate this, the sine of 90 degrees. Wait a second, we may have forgotten what that's all about. And notice that we're talking about 90 degrees. Gee, that's pi over 2. Well, gee, I'm not sure. We can go to the I'm using degrees here. I almost wrote 2 pi, but at any rate, it's the idea of, let's see, we go to the top of the amplitude like this. Okay, so we have, let's see, here's 90 degrees, there's 180. Here's 90. Oh, at 90 degrees, we're at the top of the amplitude. Okay, so the sine of 90 degrees is 1, and cosine theta. Now, cosine 90 degrees. Back to the graph. We have the graph of cosine starts at the top and comes down to the bottom and goes back to the top. Okay, at 90 degrees, it's right here as an intercept. Okay, back over here, cosine 90 degrees is 0. 0 times sine theta is 0, so this is simply cosine theta, and cosine theta appears on the right. So we have verified the identity. We're going to take a look now at 3 situations in which we use the various formulas that we're talking about in this section. And I want you to compare and contrast them. One is in the simplification process. We're just simplifying an expression. Another is to verify a situation. And a third is to solve an equation. The first one, to simplify an expression. Well, here's an expression. Now, we're using one of the formulas sort of in reverse order. This is the expanded form. We want sort of the contracted form. And we have to recognize which one this belongs to. Well, we're talking about sine cosine here, and then cosine sine. Oh, that's the sine of the sum or difference plus. It's the sine of a sum. So it's the sine of the sum of angles 140 and 50. Or it's the sine then of 190 degrees. Here's an example of a situation where we want to verify an identity. You see, so we want to verify this. Well, let's see. We just go through and rewrite cosine of the difference using the difference formula. And we're going to go through and rewrite the sine of a sum using the formula. So let's see, the cosine of a difference. Well, that's cosine of the first angle times the cosine of the second plus, remember that swapped sign situation here when cosine is involved, and then it's sine sine. So it's a sine of the first angle, sine of the second. And now we come to this part, the sine of a sum. Well, it's the sine of the first angle, cosine of the second, plus the cosine of the first, sine of the second. All right, and this is a really long-winded expression here, but let's just kind of march through from left to right and evaluate. Well, let's see, the cosine of pi. Pi. Well, we're talking about one of those major points in the graph, so we would come out somewhere and construct the graph of sine and cosine functions. Now, for the cosine, remember it kind of goes like this, and for the sine, it kind of goes like this. Okay, and this is the 2 pi position, and here's the pi position. And that's pi over 2, and that's 3 pi over 2. Okay, good. Now, cosine pi. This is the cosine curve. Here's pi. We're at the bottom of the amplitude. All right, we have -1. And then times cosine theta. Now, you may be able to imagine these. At some point, you'll get to the point where you can imagine the graphs, but for right now, we'll just physically refer to them. And the next item here refers to sine of pi. So we come back over here, here's the sine curve, and here's pi. Oh, the sine of pi turns out to be 0. So over here, this is plus 0 times sine theta, which will end up being 0 in the next step. And then we march over and we look at what we have over here. Well, we have sine of pi over 2 in this one, and we have cosine of pi over 2 in this one. All right, let's come back over here and look at the graph. Now again, we might be able to imagine this, may not be able to. Here's pi over 2. And for the, let's see where I'm looking over there at the sine curve, we're at the top of the amplitude, so that'll be 1. And for the cosine curve, it's at 0. So for the sine of pi over 2, we're at the top of the amplitude, so it's at 1 times cosine theta. And then this was an intercept, so it's 0 times sine theta. And now we go through and we clean up. Let's do it from left to right. So we have -1 times cosine theta, that's negative cosine theta. And then 0 times this goes out. 1 times cosine theta is plus cosine theta. And then let's go over here. 0 times sine theta, this goes out, and then equals 0. And sure enough, minus cosine theta plus cosine theta is 0 on the left, and we are verifying this as an identity. Here's a situation where we can use the formulas to help solve an equation. Let's say we want to solve this equation, and in order for us not to get into the infinitude idea of solutions, let's say that x is between 0 and 2 pi. Okay, so we have the sine of the sum of angles plus the sine of the difference of the same two angles, it turns out, is equal to 1. And all we do is just apply the formulas in these two spots and set it equal to 1 and just see what happens. We have the sine of the sum, so we have the sine of the first angle, cosine of the second, and then cosine of the first, sine of the second. And now the sine of the difference of angles, sine of the first, cosine of the second, minus the cosine of the first, sine of the second, equals 1. And now we want to kind of step back a little bit and look at the whole thing algebraically. Now I recommend that you do that in solving equations and maybe even in simplifying as well. And I didn't mention it before, but sometimes you can get some mileage out of just looking at the big picture rather than going through and identifying the value for cosine pi over 3, for example. You might get some value out of looking at, for example, the notion that we have cosine x sine pi over 3 minus cosine x sine pi over 3 here. So those two terms take each other out, and we don't have to bother with evaluating sine pi over 3 in both of those two cases. All right, now it's a matter of looking at each of these and deciding about value. Oh, wait a second, I'm noticing that they're the same. So we have sine x cosine pi over 3, sine x cosine pi over 3. That's 2 sine x cosine pi over 3. You see, so again, we're looking at the algebraic form, and now we go through the evaluation process. Now, cosine pi over 3, we would refer to one of our little triangles and whatnot, and we find out that that turns out to be 1/2. This is the same as 60 degrees if you'd prefer to think of it like that. But at any rate, so it's 2 times 1/2. Oh, half of 2, that's 1. So this is simply sine x equals 1. Sine x equals 1. We want the angle whose sine is 1. So again, we jump out to the side and we look at the sine curve. And the angle whose sine is 1 is this angle. The x value whose sine is 1 is right here. This is pi. That would be pi over 2. So x then is pi over 2.